Hi guys, this is Vicky here again, and we are now going to talk about how to determine if an acid and a base is strong versus weak, okay, in regards to its equilibrium. So let's talk about the strong acids first. So let's just assume that here's a solution of 10 molarity HBr. Let's just say 10 couples of HBr, which we know for a fact are strong acids, but let's just say we don't know, come to a pool party, okay? So 10 couples come to a pool party. What happens is the second these strong quote unquote acid couples hit water, they start to completely ionize. So all 10 of them are actually going to completely ionize and split apart. Okay, I don't think I have enough space to draw all 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so they all start to break apart. All right, so they are all breaking apart and they are no longer in a couple relationship. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so all 10 of them broke apart. That is basically the idea behind a strong acid versus a weak acid. And obviously it holds true for bases as well. This is why we use an arrow that's going straight. It's not a double arrow, okay? So this is where we bring in the ice table. Okay, initially, change, and at equilibrium. So I always tell my kids, okay, so basically, initially, 10 couples show up to a pool party, right? You have 0 solo boys and 0 solo girls, okay? And during change, during the pool party, all 10 of them break apart, creating 10 solo boys and 10 solo girls. Okay, so at the end of the pool party or at equilibrium, you have no couples, you have 0 couples left, you have 10 solo boys and 10 solo girls. So that means if I were to plug it in into my pH equation, it's going to look like this, right? So these are going to be solo boys, right? That gets plugged in there, and we can now do the calculations. Does that make sense? Cool. Now let's quickly talk about the weak acids and how that works. So weak acids, okay, so weak acids, it's a little bit different in the sense that here's the pool party and let's just say 10 molarities of HF show up. HF being weak acid, we know that, but we're now going to talk about its concept behind it. So 10 couples of HF show up. But the problem is all 10 of them are still going to go strong and they're not breaking up. So it's like, what the heck? None of them are breaking up, right? And barely like one of them would break up, right? And only one of them breaks up, creating this arrow that goes back and forth. So I always tell my kids, think of it as this. Weak acid and bases, they are so weak that they don't know how to fly solo anymore, that they are so dependent upon each other that they have to be stuck to each other, okay? So again, if 10 couples show up to a pool party and we have 0 solo boys and 0 solo girls, out of here, less than 5% will break up. Okay, so less than 5% breaks up. So a maximum of 5%, okay, of the original couple amount, right, is going to go solo. That means that this 5%, it's almost negligible. It doesn't really make a dent in the couple pool. So that's why we are able to ignore this. Okay, it's negligible. We ignore that and we just say, hey, barely no one broke up, then they're going back and forth between couples. So at the end of the day, no one really broke up. And we barely made any single boys and any single girls, right? So if I were to plug it in into my pH equation, okay, again, I barely made any solo boys and solo girls. So that number is going to be very, very, very low. Does that make sense? So now let's continue and let's talk about them in regards to the Ka values, okay? So here, Let's talk about them in the Ka value scenario. So if I were to talk about them in the Ka value, okay, what happens is, what is Ka? Ka is the solubility of acid and bases, right? So the solubility of acid and bases, so Ka, it's always going to be products over reactants. So H plus over Br minus over HBr for the strong acid. And for the weak acid, it's going to be H plus F minus over HF, right? Okay, now if you look at this, what happens is we are going to plug in all the numbers that are at equilibrium. These numbers are the ones that are going to get plugged in. So if you look, I am going to plug in 0 HBr because I don't have any couples left for the strong one. I am going to plug in 10 into the H plus and 10 into the Br minus. Hence, you know, like when you do the calculations, you're like wondering, why is it always x squared over this and then there's no Ka value for strong acids and bases? This is why, because you're putting a 0 in the denominator and that doesn't really exist. So there's no real equilibrium per se. Everything goes to product. And we are creating a 1-to-1-to-1 ratio, or whatever ratio this acid has, stoichiometric ratio of acid and bases. So this is why the Ka value is very, very, very high. Versus in the weak acids, I am going to put a 10 down here, basically the full original value of the acid couple that came in. Okay, less than 5% here and less than 5% there. Now this less than 5% can be 0.000000001%, or it can be 4.9999999%. It can be anywhere in between 0 and 5%. So this is why they give you the Ka value and they ask you to do the calculations. Okay, hope this makes sense, and let me know if you guys want any extra videos explaining this further. I have a couple more videos with some real problems from College Board AP Chemistry FRQs, so feel free to look into them and don't forget to subscribe. Bye guys!